Hi, everyone. In this section, we're going to look at 3.2 on polynomial functions and their graphs. So first, let's talk about what a polynomial function is. It's obviously a function, and it's a function that's also a polynomial. So for a polynomial, they look something like this. This is the general form here that you would see. And then these would all be powers. And what you want to note here is that for your powers in a polynomial function, the exponents actually must be whole numbers. So for our exponents, we're not looking at any fractional exponents or any negative exponents here. The other thing you want to know is that in a polynomial function, the highest power tells us actually a lot of information. It gives us the degree of the polynomial. This is a little side note here. In X, so if you have just one variable, that highest power will give you the degree of the polynomial. And that highest power also contains the leading coefficient. And the leading coefficient is that first number that's associated with that highest power. Now, for a degree, we're going to do more with this later on, that kind of leading power there, because it can tell us a lot of information about the graphs of polynomials, but also the degree will tell you how many solutions you could possibly have if you were solving an equation. So here we're kind of going to focus on graphs and things, but if you were solving an equation, that degree is really nice because it tells you up to how many real solutions you can have. So it would tell you up to how many x-intercepts you could have, for instance, with that example. So a couple things to note here. So things that are polynomial functions, just a couple examples, could be something like -6x⁵ plus 4x cubed plus 3x squared minus x plus 7. Okay, so notice all my powers are whole numbers. They are typically in descending or decreasing order, so we do like to write things in order. Negative numbers are fine, or even negative fractions. I can make this 3/2. That's fine. So the numbers can be anything they want. It's just the powers that we focus on. Something that is not a polynomial, for instance, or a couple things. Let's say you had the square root of x minus x squared plus 4. That's square root of x, not a polynomial. Or maybe if you had something like x to the 1/3 power, again, not a polynomial. 1/3 is also the same thing as a root. Other things that are not polynomials, let's say you had an exponent that had a negative. That is not a polynomial. Or let's say you had a variable in your denominator, also not a polynomial. And these two are related. Variables in the denominator and negative exponents relate to the same thing. So your polynomial function is really sort of like the next nicest function. We kind of have the linear as the easiest ones, then our quadratics, which have the squares, and then the next kind of nicest function are your polynomial functions. Now, with graphs of polynomial functions, if they have degree 2 or higher, they are smooth and continuous. So by smooth, we mean that the graph only has rounded curves, no sharp corners. And by continuous, we mean that there are no breaks, no holes, no gaps, nothing like that. And the big thing is that you can draw it without lifting your pencil. That's a great test. So if you can draw a graph, like trace the graph without lifting your pencil off the paper, then it's continuous. If you have to physically lift your pencil up to jump over a hole or a split or something like that, it would not be continuous then. It would be called discontinuous instead. So for instance, and I'm just kind of drawing these from your text. That was easier just to draw them in this time. So something like this could be a polynomial function. It's continuous, right? There's no holes, there's no gaps or anything, and all my curves are smooth. So I don't have any pointed or jagged edges there. Or maybe something like this. So this would be a little more curved here. But you know, can have multiple U's, multiple dips and curves and things like that is fine as long as everything is nice and smooth. So this should be a nice smooth curve here. Things that would not be polynomials is anything that has a break or a split in it. So let's say you have a graph and maybe it goes like this, and then we have a hole here, and then it jumps up to here, right? That clearly has a hole or a split in it. You can also see a split like this. So you may see a graph that looks like this, and then maybe you have a split. So somehow it splits, right? You have a split here, or maybe you have a vertical split. So things like this are not polynomials. Or maybe you don't have a split, but maybe you have some kind of jagged pieces. So maybe your graph starts low, and then instead of having a nice curve, you kind of have this spiking motion here instead. So again, not a polynomial. So it should be nice, smooth curves. Now in this section here, there's really a lot of different kind of mini tests that we're going to look at. We can really pick out a lot of information about a polynomial's graph just from its equation and vice versa. So if we know a little bit about the graph, we can find a lot of information about the equation and then the other way around as well. So I want to talk a little about the end behavior of a function. So that means what's happening on the ends of the graph. So as you go off to positive infinity and off to negative infinity, what's happening at the end of those graphs. So either looking to the far left as you go to negative infinity on the x-axis, or to the far right as you go to positive infinity. And we have something called the leading coefficient test. Okay. So here's your polynomial function. And then basically with polynomials, one of four things are going to happen at the end of that function. So first here, you want to notice that n is odd. So this is your degree or your highest power. Okay, so when we're talking about n here, we're referring to that initial kind of highest power of our polynomial. So if that initial highest power or degree is odd, then what happens is your graph does opposite things on opposite sides. Either one side goes down, the other side goes up, or goes the other way. One side goes up and the other side goes down. So when you have n is odd, you're going to see that, again, one side will go down and one side will go up, or the other way around. This side looks up and this side kind of points down. Now, a whole bunch of things can happen in the middle. So that's why you just have dashed lines here, just to show you that I don't know what's happening in the middle. This is just the end behavior, but we can tell a lot right away just based on that degree. The other thing we look at is the coefficient out front. So this A is that leading coefficient there. So if that leading coefficient is positive, then it's going to go this way. And if that leading coefficient is negative, it's going to go this way. When your n is even, what happens is both sides do the same thing. So they're either both going to go up if your leading coefficient is positive, or they're both going to go down if your leading coefficient is negative. And again, I can't tell you what's happening inside the graph just from this information, but I can tell you what's happening on the ends. And sometimes this is really important. A lot of times we like to predict what's happening with things. So particularly I feel like this right-hand side, as we go to positive infinity, tends to be really important. If we could figure out that overall direction, a lot of times that helps us with applications a lot. Okay. Now in your book, you do have a nice little chart summary here that I'm just going to copy over for you, but whatever works. So I kind of like a larger chart. I find that easier to work with, but if you like a smaller chart, this one is in your book and it's kind of nice. So if n is odd and your A is positive, then what happens is the left side goes down and the right side goes up. If your n is odd and your A is negative, it's going to be the opposite way. That left side goes up and the right side goes down. If your n is even, they're going in the same direction. If it's positive, they're both going up. And if it's negative, they're both going down. So this chart here says the same thing as the pictures do. And whatever you find most helpful, you can go ahead and use that. So let's use the leading coefficient test to determine the end behavior of the graph of this function. So do notice that my powers are descending, which is really helpful. We do like to write our polynomial as descending. So right here, I can see that my degree or my highest power in this case, is equal to 3. And I see that my leading coefficient is 1. So if there's no number there, there is a 1. So my leading coefficient is positive. Okay. So what's going to happen here? My highest power is odd, right? And then my leading coefficient is positive. So I know that the left side is going to go down and the right side of my graph is going to go up. One second, guys. Sometimes what we'll say too, and this is getting a little bit more into the upper level mathematics, is what we'll say here is as x goes to negative infinity, so right, we're going towards the negative side, the graph falls, meaning it's going down. And on this side, as x goes to positive infinity, the graph rises. So again, just another way to say it. This is kind of new notation that your book doesn't really stress too much, but this just means as x goes to negative infinity. So as you're going smaller and smaller and smaller for x, that graph is going down on the left. And as x is getting bigger and bigger and bigger, that graph is going up on the right. So it's just some new notation and something that you see a lot in upper mathematics. All right, let's do another one. So again, use the leading coefficient test to determine the end behavior of the graph. Now, this one's a little bit different here. So it's not multiplied out, so it's a little bit hard to see. So what you can do here is one, you could multiply everything out, but that does take a lot of time. So you could actually find your degree or that exponent a different way. And you basically put all parts together on your variables. So here, notice that you have a power of 3. Here you have a power of 2. And if there's none written in, you do have a power, it is 1. So what you do is you add these together. And we get a degree of 6 here. So, and this is going to be your degree. So your highest power, or your degree in this case, is equal to 6. Now the number out front is still going to be your leading coefficient. And that's because all these other x's just have multipliers of 1. So it's not going to change that kind of leading coefficient there. So your leading coefficient is -4. So when our power is even, I know that we're going to go the same direction, either both up or both down. And when your leading coefficient is negative, they're both going to go down. So this way and this way. So we can say it a couple ways. We could say as x goes to negative infinity, the graph falls. And we can say as x goes to positive infinity, again, the graph falls. In this case, it goes down. The way your book says it, they write the sentence like this. It says, the graph of f falls to the left and to the right. So instead of using negative infinity and positive infinity here, they refer to as left and right, right? So negative infinity is on the left side, positive infinity is on the right side. So just another way to say it. And this is what you'll see more in your text, but realistically, if you're looking more on videos online or in other textbooks, we tend to use that other notation instead. All right, let's do a couple more examples with the leading coefficient test here. And these ones, I just brought in the work from our textbook to make it easier for us to talk about. So let's talk through them and talk through the answers there as well. So HIV remains a persistent problem for the United States and countries around the world. According to the CDC, at the end of 2020, an estimated 1.2 million people in the United States had AIDS. Using a limited portion of the data shown by the bar graph, we developed the following model for the number of Americans with AIDS, X years after 1983. Use end behavior to explain why this model is only appropriate for a limited time period. Okay. So first of all, let's actually figure out what the end behavior would be. So we're using that leading term. Everything is multiplied out here, so it's a little bit easier to see. So I see my degree is 3, which is odd, and my coefficient is -49, so that's negative. Now, if you need to go back to the page before to see that chart, you can go ahead and do that. So when n is odd, or when n is odd, and that leading coefficient is negative, we see that it's going to rise on the left and fall on the right. So our graph is going to kind of be up this way and then fall on the right. Okay, and that's what your book is saying right here. Now, when we're falling on the right, you want to remember that with polynomial functions, they keep going forever, right? So all the examples that I've shown you so far, those ending values, those ending behaviors continue forever in that direction. So this polynomial will continue falling forever and ever and ever and ever and ever. But really, in an application problem, that may not make sense, right? So if we think about it, although the graph falls to the right, indicates is falling to the right, at some point, the number of A's cases will be negative then, according to the model, right? If you really let it keep falling, eventually you're going to hit negative numbers there, which doesn't really make sense for an application. So if a function has a graph that decreases without bound over time, it will not be capable of modeling non-negative phenomena over long periods. And that's the idea here. So we can use it to model within a short range, but we do have to note that because it's a polynomial function, it's going to eventually keep falling forever, which is not going to make sense for our application. So when we do model, and we've mentioned this before, you always have to keep in mind how relevant that model is and for how long. So usually we don't go too far past our data for our models. You know, this starts in 1983, so maybe I'll do a few years past my last data value, but I probably am not going to go out 20 years or 30 years here, right? That would be too far. So our models at some point usually do end up breaking down if we go too far outside the initial data range. Okay, so that's why this model is only appropriate for a certain amount of time. Let's talk through another example. So if you're using a graphing utility to graph a polynomial function, so maybe you're a graphing calculator or a Desmos or something like that, it's important to select a viewing rectangle that accurately reveals the graph's end behavior. If the viewing rectangle or window is too small, you may not actually see the end behavior. So perhaps you don't actually see the end of the graph. So you have to be really careful here. Make sure you zoom in and zoom out on that graph just so that you know where the end behavior actually is. If you're too zoomed in, you may actually miss the end behavior. For instance, if I go back to the page before, so let's say I was looking at this graph here, maybe my polynomial did actually look like that. But if I was zoomed in too close, maybe I was zoomed into here, it would look like it was falling on both sides, right? I wouldn't actually see that on the left, it actually rises. So you need to be careful when graphing that you have the right viewing window. So here on the left is the graph of negative x to the fourth plus 8x cubed plus 4x squared plus 2. And it was obtained using a graphing utility. And this is the viewing window. So your x values are going from -8 to 8. The scaling is by 1. And the y values are going from -10 to 10. Again, the scaling is by 1. So our question is this a complete graph that shows the end behavior of the function? How can you tell that you actually have a good enough graph? And we can use the equation here to help us. So notice in our equation, our degree is 4. And our coefficient, our leading coefficient there, is -1. So if you go back to your chart, our degree is even. So when I have an even degree, both ends should either be going up or both should be going down. My coefficient here is negative, so both ends of my graph should be going down. So the end behavior of the graph should be falling both left and right. If I look at this viewing window, I can tell right away that I'm not seeing enough of the graph. I know based on the equation that both sides should be falling, And here it looks like this side is falling, but this side is going up. So what's happened is I've zoomed too far in on the graph so that I can no longer see that end behavior there. If we graph it, I'm just going to bring over your text here to save from going into Desmos for a second. But if you graph it, bear with me for 1 minute, and zoom out a bit. So here at this viewing window, they're going from -10 to 10 on the x-axis. And then they're going from -1000 to +750 on the y-axis. You can now see that the end behavior matches, right? It's going down on both sides. So this graph is working much better, right? This is more accurate versus the other one, which is a little bit too zoomed in. Now, if you were looking for information about a particular part of the graph, like around maybe the origin, then that's fine. But if you're actually hoping to see the entire graph, you do need to make sure that you have a good viewing window so that you can see the whole thing. Or you won't be able to see the whole thing, but at least the general pattern of the whole graph, I should say.